In this video, I'm going to talk about something that I personally think very cool. So we are going to construct the optimal simplex table without going through all the iterations. So we are not going to perform the error or elementary row operations, yet we are able to construct exactly how the optimal simplex table look like. It's very cool, right? So let's start. To construct the optimal table of a linear programming, we have to have this information. First, we need to know which variables become basic variables in the optimal table. In other words, we need to know the optimal basis. And then second, we need to know all the parameters in the original problem. Okay, so we need two information to create the optimal table of a linear programming: the basis in the optimal table and all the parameters in the original problem. So here's a generalized model of linear programming. We want to maximize z, and then our decision variables are x1, x2 up to xn. And here actually x may be also slack variable, excess variables, artificial variables, or whatever. We just denote them as x here. So we have x1 up to xn. And then the coefficient for each variable in row 0 is denoted by small c. Now for the constraint, the right hand side all denoted by the small b. So B1 is the right hand side for the first constraint, B2 for the second constraint, up to Bm. So we have m constraints, we have n variables. Now for the parameters in the constraint here, the coefficients I mean, for example, A21 means the coefficient of the second constraint with respect to first variable. And up to, let's say, amn means the coefficient of the mth constraint, the last constraint, with respect to the nth variable, the last variable. Okay, so to recap, c is the coefficient of a variable in row 0, b is the value of the right hand side of the constraint, and then a is the coefficient of the variable in the constraints. So here's an example of the Dakota problem, and then you see that a C1 equals 60, C2 equals 30, C3 equals 20, and then C for S1 equals 0, C for S2 equals 0, C for S3 equals 0. And 48 is B1, 20 is B2, 8 is B3, and then let's say this is 1.5 is A32, because this is the coefficient for the third constraint with respect to the second variable. Okay, so those are the notations that we are going to use. Now let's talk about XBV and XNBV. So if we define the basic variables in the optimal tables are BV1, BV2, and BVM, because we have M constraints. And then we will have the XBV, simply the collection of those basic variables. So this is the set of all variables that becomes basic variables in the optimal table. And then we need to keep the order of these basic variables as such they appear in the optimal table. So if in the optimal table, the first one, let's say, is S1, so we need to put S1 as the first basic variable. If the second basic variable is, let's say, X3, then we need to keep it that way. And the last one, X1, we need to keep the order. You do not want to reorder them, okay? And then X and BV simply means the vector that lists all non-basic variables in any order. So let's look at the optimal table for the Dakota problem, and then XBV is S1, X3, X1 in that order. Okay, And then x and bv is you just put all the variables that are non-basic. So we have x2, we have s2, we have s3. Okay, so x, bv are the collection of all basic variables in the optimal table, and x and bv are the collection of all non-basic variables also in the optimal table. Now we have c, bv, and c and bv. Remember that the small c corresponds to the coefficients of the variable in row 0 in the original problem. So CBV simply means we collect all values of the cost of the variable that becomes basic variables in the optimal table. Okay, so let's say we know that our basic variables are S1, X3, S1. For the CBV, we collect the cost of S1 is 0, the cost of X3 is 20, the cost of X1 is 60. So here's our CBV. Again, the order must follow the order of the basic variables, 0, 20, and 60. 0 is for S1, 20 is for X3, 60 is for X1. Then C and BV simply the cost of all the non-basic variables. The cost of X2 is 30, S2 is 0, S3 is 0. Again, you see this cost from the original problem. Next, we have B and N. So M by M matrix B is the matrix whose jth column is the column for basic variable j. So again, if we know that our basic variables are S1, X3, and X1, so this B means that we collect all the columns corresponds to the basic variable, the column in the constraint part. So we collect that column for S1, we collect the column for X3, we collect the column of X1, and then we put them in order. So S1 first because it is the first basic variable. X3 goes to the second column because it is the second basic variable. And the third basic variable is X1. So this column of the constraint of X1 becomes the third column of B. For N, we simply take all the columns of the non-basic variables. So the first column is the column for X2 because X2 is the first non-basic. The second is for the column of S2, and the third one is the column for S3. Now for small a, j, and b, remember that small a is about the coefficient of variable in the constraint part, and that small b is the value of the right-hand side. So a, j is the column of the constraint for the variable j in the original problem. So again, that is our Dakota example. And then let's say if you want to find out what A2 values are, so you just need to check the column of the variable x2, so 6 to 1.5. And then A for S1, you take the column for S1 is 1, 0, 0. Okay, so AJ simply means the column of a variable in the constraint part for variable j. For small b, it is the vector that shows all the value in the right-hand side of the constraints. So here in the Dakota problem, we have b equals 48, 20, and 8. Now, once we have defined all those notations and how to get the values for each of those notations, we may then use all those notations to construct the optimal table of a linear programming model. We are going to discuss the construction of the table in 4 parts: the construction of the constraint part, in the variable side, the construction of the constraint part in the right hand side, and then the construction of the row 0 in the variable side, and then the construction of the row 0 in the right hand side part. Okay, we are going to do that in the next two videos. So see you on the next one. Thank you.